Hello, everyone. Let's continue with the lecture. This is going to be a kind of a supplemental lecture, kind of a fun one here. And we're going to talk about misuses of statistics. We're going to talk about ways that stats can be misused to mislead you, to kind of make things seem like they're not. We'll actually just have a lot of fun examples today. So let's go ahead and get into this. So starting off with sampling, remember we've talked about that when we're trying to study a population, if we're trying to study every single person that walks into a grocery store, that's going to be tough to do. You might not be able to ask the questions that you want to every single person in the grocery store. So what you could do is you could do some form of sampling, which would be, hey, let's pick a subset. Let's just pick part of that entire population. Let's just pick some people that are in the grocery store. And hopefully, if you sample appropriately, the people that you ask are representative of that entire population. And so you can take your results and you can extrapolate them to say, hey, everybody in the grocery store basically follows the same trends as the people that I asked, the handful of people that I asked. So we've got sampling here. We've seen a couple different methods of these. Let's talk about some poor sampling methods, some ways that you could sample that are bad. So the first thing that we're going to look at is not reporting an actual sample size here. So let's say that we take a sample, but we don't actually say how many people reported or were sampled. So if I just said the statement, 5 out of 5 of my students have an A. Well, what if I just the way that I sampled was I asked the students that stayed late after class to ask questions. Maybe there's a trend that the students that were to do that would, you know, tend to have an A. Maybe I just happened to ask the 5 students that had an A. And if you have no idea how many students I've sampled, you don't know if these stats are accurate. What I could even do, this would be very misleading. I could just ask one student. I could say, "Hey, what's your grade?" And they could say, "Oh, I have an A." And I could then say, "Oh, great, 100% of my students have an A." And I don't tell you that I only asked one of my students. And this obviously doesn't make sense. You hopefully wouldn't do this, but sometimes this happens. You hear this a lot with dentists and toothbrush commercials. Say 5 out of 5 dentists recommend this toothbrush or this toothpaste, and you have no idea how many they asked. Did they ask 10,000 of them and they all said yes? Or did they just ask 5 that they happen to know would say that they like their toothpaste? So, not reporting sample sizes is a big issue. Let's move on. If we take a sample that relies on volunteers, this can be bad in certain scenarios. So, your results can be skewed in a scenario such as this. In an on campus study on sleep deprivation, we paid participants $50 to stay awake for as long as they could. We found that 9 out of 10 people are able to stay awake for 24 hours straight. There's actually a lot of things wrong with this. First things first, the term on campus makes it seem like it's college students. And if it is, in fact, just college students, students in college are probably a lot more likely to be able to stay awake for a long time than just the general population. And so saying on campus and then relating this later to just saying, oh, it's just 9 out of 10 people. It's just everybody, 90% of people can stay awake. Well, you only tested college students. So that's not a representative population there. Also, in this scenario, you're paying participants $50. And so the people that volunteer for this are probably people that are likely to either need that money or want that money, which that could skew your sample, because if you're only, maybe you're now only looking at people who need that money or who want $50. You're also, because you're talking about volunteers, you're also likely only to get people that know that they can stay awake for a long time. If you were someone who had a very hard time staying awake for 24 hours straight, if you're not a night owl, you're probably not going to sign up for a study on sleep deprivation because you just know that you can't do it. And so the fact that you have volunteers for this means they're likely already pretty good at staying awake. And so the people that you're sampling are not representative of your entire population, especially if they're college students who want money and are good at staying awake. That's not representative of the entire world or the entire population that you might be trying to sample. So volunteers can mess things up. You got to be very careful if you were to do a study with volunteers. Let's continue on. Opinion polls are very common. So if we have sampling that's carried out by people volunteering, and when I say that, generally what I mean is if people are optionally able to review something, then the people with strong opinions tend to participate more than others. And a great examples of this are Yelp or really any sort of review-based site that you have there, Google reviews or anything like that, anything that has a review on it. What you tend to see is you tend to see a lot of 1-star reviews and you tend to see a lot of 5-star reviews. And so a lot of places just end up right in that middle range of 3 stars on average because they end up just having very opinionated reviews. You're likely not going to review something if it was just very mediocre, very in the middle. If something is actually 3 stars in your mind, you're very unlikely to actually take the time to go review it. But if you had a very bad experience, say at a restaurant, or if you had a very good experience, you're likely to want to tell other people about that. And so in this sense, when you're taking people's opinion in a survey, in a study, that can mess things up because you tend to only get people that have the strong opinions to actually respond. So you got to be careful there. Moving on, convenience sampling, and rather than kind of these other things that we've seen, which are just things that can happen poorly, this is an actual way of singling out people that you want to talk to, and that way of singling out, it's not random, it's not clustered, it's not stratified, it's not systematic, it's convenient, however. So let's say that we were considering this following scenario. A resident of downtown New York asked his neighbors whether or not they owned a car. And then that resident determined from the results that 2 out of every 7 people own a car. Well, this stat, you can hopefully tell, is just not accurate at all. And there's a couple reasons for this. First off, this person lives in downtown New York and is asking his neighbors if they own a car. And a lot of people in New York don't necessarily own a car. They may take public transportation, or they may walk, or they may bike. And so this population that this person is studying, the people that he's asking are not representative of everybody because they live in downtown New York. And so they're much more likely to not own a car. But the thing is, this person has sampled, he has gone out and asked these people based on convenience. It was just convenient for him to just ask his neighbors. He's not going to go fly to a different state or go to a different city where there's more cars and ask people because it's just not feasible for him to do that. So he's just asking in a convenient sense people that live near him, and that obviously skews his results here. So convenience sampling, you're going to want to group that into those other 4 types of sampling that we've seen and recognize that when you see it. All right, so moving on, we're going to talk about how statistics can be sort of misleading. So not so much sampling anymore, but just looking at statistics. And we'll look at a couple different ways that they can be misleading, exactly. So first things first is ambiguous averages. And a very easy way to talk about this, a very simple scenario, is just saying a typical employee of our company stays here for 5 years. Well, there's a handful of questions here. First off, what do you mean by typical? Do you mean a typical part-time employee? Do you mean a typical full-time employee? Do you mean a typical employee that has a certain level of experience? What do we mean by typical? There's a lot of ambiguity there. But then also when we say that they stay there for 5 years, there's no indication of what this 5 years actually is. Is it the median? Is it the mean? Is it the mode? We have no idea what we actually mean by 5 years. You could maybe you just have, you know, 3 employees that have been there for 5 years, and then the rest of the employees have been there for a different number of years. And so 5 is your mode. And then you could say, hey, a typical employee stays here for 5 years because you have more employees there for 5 years than any other number of years. And so it can just be ambiguous because in this scenario, at least, we don't really know if we're talking about mean, median, or mode. And so that's where we get at with ambiguous averages. This sentence here makes it seem like 5 years is the average, but it may not be. It could be the mode or the median. So we got to be careful there with our measures of central tendency. All right, using percentages versus numbers. What you might have in this scenario that I've written here, maybe a politician is talking about their time in office, and you could say, during my time in office, I increased spending by 3%. And that sounds like a statement. That's fine. 3% doesn't seem like a whole lot. In the context of 100%, relative to the 100%, 3% is pretty small. But if in a different light, you said this as during my time in office, I increased spending by $10 million. That number is just so large that even if $10 million is 3%, even if these are exactly the same thing, using that raw number or using the percentage can change the connotation of what is meant. It can change what people think about it. When you just see 10 million, it just seems large. So in this statement, someone's going to say, oh, they increased spending a lot. In this statement, they're going to think that they didn't increase spending very much. Yet they very well could be the same exact value. Maybe 3% of the spending is $10 million. So you got to be careful using percentages versus raw numbers. All right, detached statistics. This happens all of the time on really any product that someone is trying to sell. Just you'll see this statement, our brand of crackers has half the calories. And the question here is, well, half the calories of what? Is it half the calories of another brand of crackers? Is it half the calories of your brand of crackers that they used to be, and maybe you've made a new box and now you say it has half the calories? Is it half the calories of an elephant? Who knows? I mean, we have no idea what they're referring to. Obviously, a lot of times you could probably surmise that they're talking about it's half the calories of a competitor brand of crackers. But in this statement here, we don't really have any idea exactly what they mean by half the calories. And this can get a lot more tricky and a lot more important than just when you're talking about brands of crackers. This stuff happens all the time with really any product that is trying to be sold. So stating a stat and not saying a reference to it, it just makes that data meaningless. So be careful of detached statistics. Watch out for those. Also, implied connections. Got to be careful here. So what you can do is you can imply a statistic. You can imply stats without actually saying them. So if I say something like studies suggest that bribing your teacher will get you a better grade, this seems to imply that because I just say studies suggest, this seems to imply that I've gone out there and I've actually surveyed people. I've actually gathered data and figured out that bribing your teacher will get you a better grade. But I don't actually state that here. I'm just saying that studies suggest it. And a lot of studies may suggest it, but it might not actually be true. It would depend on a lot of factors, obviously. But here, just saying studies suggest, it gets people to think that the data is there, even if it's not. So you want to be careful on implied connections. One of these last ways that we can, be misled by data is if we're dealing with a survey question, and the way that it's asked can be very misleading. It can skew results. So Maybe we go ask someone in a survey, are you going to vote for candidate Smith, even though the latest survey shows he will lose the election? This has been done before. If you ask people this type of question with this connotation of, oh, even though he's supposed to lose, people actually say that they're going to vote for them less than they normally would have. Just skewing this into saying, oh, even though he's going to lose, it forces people to get into that mindset of, oh, if he's already going to lose, I don't want to vote for him. And so they actually tend to say, no, they're not going to vote for this candidate more often than if you were to just say, are you going to vote, and just leave it there. So the way that survey question is asked definitely skews your answer. So you could also skew a survey question by saying something like this: are you in favor of more homework, and do you think that this would help increase your grade? And this is very natural to answer yes to this, because the way that I've stated this, I've finished this statement, this question, with, do you think that this would help increase your grade? And when you hear increase your grade, you're thinking, yeah, I want to increase my grade. And yeah, I agree that more homework will probably increase my grade. But the question here has an and this is where logic comes into play. Are you in favor of more homework, and do you think that this would help increase your grade? And so the way I've asked this question, the only scenario where you should say yes to this is if you actually are in favor of more homework, as well as if you think it will increase your grade. So a lot of people will say yes to this, just assuming that they're answering one part or the other part. And this leads to a lot of skewed results here, because then whoever's asking this survey, they can just say, oh, a lot of people said yes, they're in favor of more homework, and they think it'll help increase their grade, even though you may not have been thinking that you were answering yes to being in favor of more homework. So these double-sided questions, these questions that it can involve logic, ands and ors, or even if-thens, or if and only ifs, you got to be careful about those. Continuing on with this idea of logic, we can talk about negations, and negations can make things very tricky. So maybe I ask a question: do you think that we shouldn't have more areas where people can't smoke? And in the way that this is phrased, there's a lot of double negatives in here, and it's honestly just confusing what I'm actually asking. If you were to answer yes or no to this, you may not be 100% sure what you're actually answering, whether you're in favor of more areas where people can smoke or whether you're not in favor of it. Just the way that there's so many negatives in here, or just this convoluted survey question, just because that question is so convoluted, it can lead to faulty answers. So you want to be careful about that. All right, now time for the fun part of the lecture. We're going to be talking about misleading graphs. So graphs are huge in terms of showing you the results of your data. We've seen this before. We've done bar graphs, we've done pie charts, we've done things of that nature. And one thing that you can do on a graph is you can change the scale of the axis. So notice here that on this axis here, we're talking about percentage of victories. This is something you don't want to do. You'd rather do this over here. But on this left-hand side, you'll notice that we start the graph at 400, at a 0.4 win percentage. And so when you look at the difference here, it looks like a lot. Just looking at the height of these graphs, of these bar graphs, it almost looks like the blue bar, like the New York Yankees percentage of victories, is 4 times or 5 times larger than the Boston Red Sox. But that's clearly not true. You can see that right there. But it doesn't look like it at a first glance, so that can be misleading. If you were to actually start this at 0 and go up, now you can really see that these are not so different after all. They're really only different by 0.11 roughly. And so this is what you'd want to do on a graph, but this happens a lot. It happens very frequently where they change the axis, and that changes the scale of these bars, and it changes what they look like. Moving on to some more misleading graphs. This is actually a very bad graph. Sorry, Fox News, but this is a very poor pie chart for a handful of reasons. First, these percentages here add up to something more than 100. And so what they're not showing here is this idea that some people actually back multiple of these presidential candidates back in 2012. And so because people actually backed multiple candidates, the percentages are going to add up to more than 100, but it doesn't make sense to make a pie chart in this scenario because obviously 70 plus 60 plus 63 doesn't add up to 100. And so you just can't make a pie chart in this scenario, but they do anyways. So that's one reason why it's bad. The other reason why this is bad is that if you look very carefully, this pie chart is actually split perfectly into three ways, even though the percentages are different. So that's just bad because here you have 70% as opposed to 63 and 60. And so this 70% should be larger in terms of area. But if you look at this, it's actually not, it's actually exactly the same. Continuing on with that line of thinking, while if you look carefully, these are the same, they don't look the same right off the bat. To me, this blue region looks a lot larger for a handful of reasons. One, the background outside of it is blue. And so this region looks just larger because there's not a definitive difference in color on the edge. The other reason is just because this pie chart is kind of tilted rather than being a straight on circle. It's kind of in an oval, it's kind of in more of an ovular shape right there. And so you can kind of see that there's some shadowing down here. And so because it's tilted, it just makes this left-hand side look a little bit larger as opposed to these red and green sections that are split right down the middle here. Lastly, what's bad here is the source. It looks like the source is opinions, which is just obviously not a good thing. You don't want opinions to be your source. You want facts to be your source. It's really opinions dynamic, but which maybe is some company or some place that ran this survey. But the problem is because their outline of their chart here cuts off the word dynamic, it doesn't look like it. And so there's just a whole lot of reasons why this is a bad graph. And also what's probably bad is that this graph is probably only shown on TV for a matter of 5-10 seconds. You really don't have time to look at it and analyze everything that we just did. What probably happens is you just look at these percentages very carefully. This blue looks a lot larger, and so you just tend to think that most people back Huckabee for the presidential candidate, when in reality, that's not actually true. So a bad graph here. Another bad graph, and this one, albeit poor quality, is just bad. First off, you've got two bar graphs here, and there's no labeling of the axes. What you can see here is it says hydrocortisone and lanacane, and then again, hydrocortisone and lanacane. Lanacane just being a particular brand of hydrocortisone. And it says 1 minute and 60 minutes, and there's no reference as to what the minutes actually mean, what we're even talking about. All we can see is that hydrocortisone decreases from 1 to 60 minutes and lanacane doesn't. So maybe if you look at this long enough, you start to recognize, oh, they're talking about the lasting effect of itch relief on lanacane versus hydrocortisone. But again, if this is only shown for a couple seconds, really all that they're trying to get you to understand here, for this 5 seconds that this graph is going to be shown, they just want you to look at the height of these bar graphs and just see giant yellow bars that say lanacane on them and think, oh, lanacane is just better than other hydrocortisones. And so that's very misleading because it doesn't even tell us what they're studying, what the actual results are. It's just trying to get you to look and think, oh, lanacane, bigger, better, cool, buy lanacane. So a bad graph here. Let's move on. This actually isn't a terrible graph other than one sort of thing here. So we've got this nice, interesting sort of picture here. We've got this nice graphic. You have a child who is injured on crutches, and they're talking about injuries that children suffer. And so you've got this kind of sideways bar graph right here that indicates all these percentages for all of these here. And you read common injuries children suffer, and you go and you start looking at these numbers, and you think, wow, that's weird. 21% of children suffer from thigh bone injuries, 21% suffer from lower leg injuries, 5% of children, 1 in 20 children suffer from spinal injuries. And the reason that this is misleading is because most people, when they read this bold, they just move straight to the graph. They don't read the underlying text, which says top traumatic orthopedic injuries. So first things first, we're only talking about orthopedic injuries, not all injuries, for which children are hospitalized. And that's the kicker. These percentages are just the percentages of children that are hospitalized and what their injuries are. This isn't all children. It's just of those that are hospitalized with orthopedic injuries, these are the percentages. But clearly, this article or this graphic is written to just kind of maybe be scary and just say, hey, look, a lot of kids have lower leg and thigh bone injuries, so be careful. But it's clearly misleading because of this subtext here that isn't bolded or highlighted. All right, here is a misleading graph. This is in all likelihood just a typo on the part of CNN here, but it's still pretty funny. It's still misleading. Should Scotland be independent? No, yes, and clearly these don't add up to 100%. As you can see, if this 5 was a 4, or if this 5 was a 6, then or if this 5 was a 4, then they'd add up. If this was 42 or if this was 48, in either of those scenarios, you'd add up to 100%. But in this case, typos can lead to misleading graphs. You got to be careful there. That you can't answer yes and no to this question. So your answers can't add up to more than 100%. All right, to wrap things up, I want to look at some correlations, and we're going to look at a handful of bad correlations. And so what we're going to see here are a handful of graphs that have 2 different things graphed on them. And you'll notice in all of these scenarios that these 2 different things that are graphed, that they follow each other pretty darn closely. And so what a lot of people will say is they'll say, oh, look, they follow each other closely. So the first thing directly causes the second thing. And there's a difference here between using the word correlation and using the word causation. Just because 2 things are correlated, just because the divorce rate in Maine, in red right here, happens to follow the per capita consumption of margarine, butter, here in the black, just because those 2 things follow each other doesn't mean that they're actually related. It doesn't mean that people getting divorced in Maine causes a larger or a smaller consumption of margarine. And so you got to be careful here, but these things are shown all the time where there's a graph here and they say, oh, so the first thing causes the second one. And it's not that it causes it, it's just that it is in fact correlated. So we've got this fairly comical there. Divorce rate in Maine, obviously correlated with the consumption of margarine, clearly not actually one causing the other though. Another example here, we've got people who drowned after falling out of a fishing boat. It happens to correlate with the marriage rate in Kentucky. Clearly not connected things, not connected instances, but they happen to follow each other fairly closely. You can see that by the graph with that trend there. Moving on, and this one is very interesting. You might say that there's some causation here. You might not want to say that, but Japanese passenger cars sold in the US and suicides by crashing of a motor vehicle. This is actually something that has been a very, very heavily debated topic, because this graph, in this specific graph in particular, has been shown, it's been stated, hey, look, when we have more Japanese passenger cars sold, there's more suicides. So clearly, these Japanese passenger cars being sold is increasing the amount of suicides. So some people claim, hey, we need to stop selling Japanese cars in the US because if we stop selling them, then the suicides will go down. And it's actually not true. They just happen to be correlated so closely that people start to think that one influences the other. So you got to be careful there because you could show someone a graph like this and convince them that Japanese cars being sold in the US increases or decreases suicides, but they're just correlated. They're not caused by each other. Another funny one here, we've got cheese consumption and the number of people who died by becoming tangled in their bed sheets. And so clearly not related, but they are correlated. They do happen to follow the same thing. So if you tried to convince someone, hey, when more people eat cheese, that causes people to die by becoming tangled in their bed sheets. That's not really true, but you might be able to convince someone of it by showing them this graph and saying, hey, look, they're correlated. So they're caused, but that's not actually the case. A common one here that you may have seen before, number of people who drowned by falling into a pool correlates with the number of films that the actor Nicolas Cage appears in. Pretty closely tied here, pretty closely correlated. Obviously, again, as I've said over and over, not caused. Just because Nicolas Cage happened to appear in more films in a given year doesn't cause people to drown by falling into a pool, but they're correlated, and so someone tries to convince people that that's the case. Lastly here, last bad correlation, the letters in the winning word of the Scripps National Spelling Bee correlates with the number of people killed by venomous spiders. And clearly, venomous spiders aren't going out and figuring out how many letters were in the winning word of the Scripps National Spelling Bee. These spiders aren't going out and figuring that out and then saying, oh, the word was longer. Okay, we got to kill more people. But they just happen to be correlated. And so with this graph, you might get lucky and be able to convince someone of this, but I'd say good luck because people would probably be able to tell that you're just talking about correlation, not causation. So a handful of fun examples there with bad correlations. We've also seen ways that graphs can be very misleading. We've also seen ways that you can misinterpret data or mislead data. And we've also seen some bad sampling methods. So with all of that there, that'll be misuses of statistics, and we'll go ahead and call that the lecture.